start. Morning to all. In yesterday's class, we discussed the effect of noise on AM system. Today, let us continue the effect of noise on other analog communication systems like a FM. Okay. Achari? Achari, can you see the board? Can you see the board?
Yes, sir.
Okay, ma'am.
Yes, sir.
Okay, ma'am, let us continue. Today, our topic of discussion is effect of noise in FM system. Okay. Noise in FM system. Okay. So as usual, we need to consider the transmitted as well as the received signal in FM system. In FM system, we're supposed to transmit an FM frequency modulated signal. Okay, and assuming the channel is ideal and it is only contributing noise. Other than that, it is an ideal with respect to the attenuation and all. That means attenuation is no attenuation is there. Okay, so then let us assume the transmitted as well as the received signal is equal to an FM signal. What is the equation of an FM signal? AC into cos 2 pi FCT plus 2 pi
FM
pi into KF into 0 to T into M of T into dt. So this is the equation of an FM signal. Okay. Many of the times we think of this as some angle function. Okay. Phase function or angle function. Okay. And we can also write this as AC cos 2 pi FCT plus, I'm calling this is a simple phi of t. Instead of using again and again, instead of writing again and again this entire form of integration and all, it is better to use a simple notation phi of t, where phi of t is equal to this much. Okay. Then what about the noise? Then the noise is white. Okay. At the input of a, along with this FM signal, noise is also received at the input of a FM receiver, and that noise is anyway as usual white noise. Okay, that is AWG noise. Okay, or whose power spectral density, because it is an important parameter, equal to eta by 2. That is a constant white. Okay. Now, some of these two are applied to the input of FM receiver. We know FM receiver is one type of angle modulation. There is another type of angle modulation, that is PM, phase modulation. Both FM and PM are closely related. Okay. This means one type of angle modulation can be obtained through another type of angle modulation. That means FM can be obtained through PM, and also we can obtain PM from FM. Okay. Based on the same logic, at the receiver also, we can use one angle modulated receiver for demodulating another type of angle modulated signal. That means we can use a PM receiver along with the additional circuitry, the required circuitry such as a differentiator. We can detect FM signal. That means instead of using directly an FM receiver, we can use PM receiver with some additional differentiator, to detect FM signal. Okay. So for that matter, let me draw the block diagram of that one. Okay. The block diagram of that one is see. So this is the block diagram. Okay. Block diagram of an FM receiver. But in this FM receiver, basically, which type of detector is used? PM detector is used. Okay. So the remaining part is except one more additional block, that is a differentiator. Remaining things are exactly similar to those of other analog communication systems like AM, DSBC, and SSB. Okay, in all those cases, we use a band pass filter and a low pass filter. These two are very, very important. Okay, this band pass filter is for limiting the noise to, or otherwise confining the noise to the bandwidth of a input signal. Okay, and also at the output also confining the noise to the bandwidth of the modulating signal. Okay, the purpose of these two filters are to confine the noise to the desired signals. If it is at input, it is input signal. If you are using at the output, we are using that output filter to band limit or confine noise to the bandwidth of message signal. Okay. Now, let me write the signal and noise after band pass filtering as usual. Okay. So, output of a band pass filter is sum of a signal component and noise component. This noise component anyway, band pass noise component. Okay. So, y of t so it is y of t equal to input signal component plus noise component. Okay. This noise component is band pass noise. Okay. Now, what about this input signal? Input signal is written as AC cos 2 pi fct plus what is the noise? Noise is band pass noise. So band pass noise can be written as AC of t cos 2 pi fct minus ns of t sine 2 pi fct. Okay. Now I'm going to simplify this noise also into a phasor like this one. Okay, here we have only a cos term. Okay, this cos term is representing an FM signal. Okay, here this noise also can be thought of as an FM signal. Another, I mean, frequency modulated signal. Okay, frequency modulated noise. Okay, another way, let me put this way. No, this here we have some cos term representing modulated carrier, and we have here band pass noise. This band pass noise is also represented in some phasor form like a cos. Then we can easily add these two by using phasor diagrams or phasor notation. Okay, so I'm going to write this AC cos 2 pi fct plus phi of t, and you see this just like a some time function into cos, some another time function into sine can be replaced with a single sinusoid with an amplitude, some function of time, and variable phase. Okay, so I can write this as En of t cos 2 pi fct plus some theta of t. Okay, where En of t equal to, see, just guess what is it? What is this En of t? This En of t is obtained from this and this. Just the last in the last session also, when I was discussing amplitude modulation, I mean noise and amplitude modulation. Okay, think of this as A. Think of this B. A cos minus or plus B sine can be represented with some sinusoid. In the same way, here we can represent. So En of t is simply equal to square root of NC of t square plus ns of
Yes.
t square under root, where theta of t equal to simply tan inverse of,
NS by NC.
oh my god, ns by nc of t. Okay, now, so why have written noise also the same form which look like an FM signal means, if you represent in this way, we can easily add these two by using a phasor concept. We can think of this is one phasor and we can think of this is another phasor. By using phasor diagram, we can easily add these two. Okay, for that matter, we are representing this form. Okay, now how to add these two? For that, let us take phasor diagram. For the phasor diagram, so this is the phasor diagram. Okay, you can easily see. You see, let me explain each and every part of this phasor diagram. Okay, which part represents which part of this equation. Okay, you see, this is a reference. Okay, and we are drawing all these phasors with respect to this reference only. First, we take up an FM signal. FM signal is a phasor whose angle is changing with phi of t. Okay, that means this is a rotating phasor. Rotating phasor. So this is represented a phasor like this, whose magnitude is AC, and rotating with the angle omega c
T
into t
phi of
plus phi of t. Okay, it's very simple. So this is a time changing angle, and AC into cos time changing angle will give us a rotating phasor. So this is a rotating phasor. Look at me here. Okay, look at this diagram. This is a rotating phasor corresponding to FM. Similarly, see, this is a rotating phasor corresponding to noise. This is added to the tip of FM phasor. Okay, because we need to add these two vectorially, isn't it? Because when you're adding two phasors, we need to add them by using vectors, a vector notation, isn't it? So when noise is added to this FM carrier, you know, we'll have a diagram like this. Then what about the resultant? Resultant will be from here to here, R of t. Okay, this R of t is having change in magnitude as well as changing angle with respect to reference as well as with respect to carrier. I mean modulated carrier. Okay, this is a modulated carrier, FM carrier. With respect to this, it is having an angle delta phi of t, and also with respect to reference, it will be having some of these two angles. Okay, isn't it? Now, when you think of this resultant, because that is y of t, here it is a y of t, I have written y of t, but r of t is the magnitude. R of t is a magnitude of the sum of these two what you call vectors or phasors. And this R of t magnitude is not constant. It is changing with the time. And also angle is changing with the time. Okay. So now we can write this equation as y of t equal to y of t equal to r of t into cos. What is the angle? 2 pi. I'm taking, this is the, because I'm comparing the entire sum of these two with respect to modulated FM carrier. So that's why phi of Ct plus angle is phi of t plus, from here to here, how much is the angle difference? Del phi of t. Del phi of t. Okay. So r of t is the magnitude of this resultant phasor, and del phi of t is the angle with respect to modulated FM carrier. Okay. So this is the resultant. So here r of t can be given by taking the components and all. Anyway, this r of t is not that much important to us, because you see, even if this r of t is function of time that is changing, you know, we can eliminate all these amplitude variations. We can remove all these amplitude variations by passing this signal through an amplitude limiter. Okay. Amplitude limiter will maintain the amplitude constant as in an FM signal, because FM signal will carry the information in the form of angle variations or frequency variations. Okay, not in the form of amplitude variations. So if there are any such variations due to the noise or some other factors, that can be eliminated by using amplitude limiter. So because of this factor only, an FM is becoming immune to noise. Okay, inherently immune to noise. Okay, why an FM system is becoming immune to noise? Inherently means because of this amplitude limiter. Okay, this amplitude limiter will remove the amplitude variations of an FM signal, which is actually created due to the noise or some other factors. Okay, that's why we are least bothered about this R of t. Okay, then what is an important factor which is bothering, which is making us more worry about, means angle variations due to the noise. Okay, so that's why, so let us find out what is its value. So I'm taking tan del phi of t. Tan del phi of t equal to how much from this diagram? Just you take the projection of en of t.
of
You take the projection of en of
del
t onto this axis. We'll be having two components. One is the cos component, another is the sine component with respect to this angle. Okay. So sine of this one, let me show. See, this is a E of n component en of t into sine, en of t into cos of this angle will give us two components. This is the cos component here, and this is a sine component. Okay. So when you take tan del phi of t, that is the angle of here. When you draw the projection of this one onto this will form a right angle triangle. So tan del phi of t equal to the opposite side. Opposite side here is the projection of this one, en of t into sine theta of t minus phi of t. Okay. So let me write that. It is en sine theta of t minus phi of t. Phi of t. Okay. Divided by adjacent side. What is adjacent side? Here adjacent side has two parts. One part is up to here, it is AC, and another part is here to here. You see, here to here, it is one part of this component AC, and from here to here, the projection of this one onto this axis is En of t cos theta of t minus phi of t, isn't it? So AC plus En cos of this angle is this component. Okay. So let me write this entire component. It is AC plus cos into theta of t, sorry, En into theta of minus phi of t. Okay. Now we can simplify this. We can simplify this equation. How we can simplify this? Just to compare just to take the denominator term, compare the two parts of the term. Okay, two parts of the denominator. One part is AC, another part is En, and En is amplitude of the noise. Okay, and normally we assume noise is small compared to signal, carrier signal. Here AC is the amplitude of the carrier signal, normally large compared to noise component. So we can eliminate, we can neglect this part of the denominator. Okay, with respect to AC. Okay, so we can write it as N sine theta of t minus phi of t divided by simply AC. This part can be neglected with respect to AC for small noise case. Okay, fine. Okay. So now we have at the input of what do you call input of FM detector, a signal component and a noise component, and sum of these two is in this form. Okay, then what about the output? Output is output of a FS detector, PM detector is an angle. Okay, so output V of t is simply equal to, if you look at PM detector, output V of t is a term or voltage proportional to the angle of the input. This is what a PM detector will do, isn't it? A PM detector detects the angle of the input modulated signal. Okay, so sorry. So if you write it as the output V of t is equal to the angle of first one. What is the angle of first one? Phi of t plus the second part is del phi of t. This is the output of PM detector. PM detector. Okay. So from this we need to find out the other terms. Okay. So now when this signal is allowed to pass through a differentiator, will have an output V of t after also passing through low pass filter. So now signal component is simply equal to, what is signal component? This signal component after passing through differentiator S naught of t is given as a differentiation of which one? Phi of t. And it will also have some constant of proportionality. I'm writing it as some kd. And what is this? Simply kt. And what else? What is a phi of t? Phi of t is 2 pi kf integral 0 to t into m of t dt. Okay. And you see this kd. After differentiation, what happens to this? Is 2 pi kf into m of t. And assume let kd equal to 1 by 2 pi. Then what happens when kd equal to 1 by 2 pi? So S naught of t is simply equal to 2 pi will get cancelled, giving us only kf into m of t. So from this we can calculate output signal power as S naught in square, which is equal to kf square m square of t mean, which is equal to kf square into PM. P sub m. P sub m means modulating signal power. Okay. In the same fashion, we need to find out output noise power also. But instead of finding the output noise power from its noise power spectral density, we will find out noise power spectral density at the input of a differentiator. And then by using transfer function of the differentiator, we'll find out the noise power spectral density at the output. Okay. And from that, we can calculate noise, output noise power. Okay. So for that, let me take this equation. Okay. So input of the differentiator is what? Input of differentiator is del phi of t, isn't it? And this is equal to, okay, this is equal to n by AC sine theta, is it theta? Theta of t minus, it is theta of t minus phi of t. Okay. Now, this is the signal at the input of the differentiator. Okay. So instead of finding directly the output of the differentiator from this input, let us find out here itself it's a noise power spectral density. Once its power spectral density is found through, by using a transfer function of the differentiator, we can find out its output noise power spectral density. From that, we can calculate the noise power easily. Okay, that's why. First, let me simplify this. Here, there are two angle variations. One is due to the message signal. One is due to the, here, see, there are two angle variations. One is due to the message signal and other is due to the noise. We know, sorry, one is due to the noise and other is due to the message signal. Okay. So this is due to the noise, this is due to the message signal. We know the noise is very random and high frequency. So these angle variations are very large compared to these angle variations. That means compared to the angle variations due to the message signal, the angle variations due to the noise is very large. So as far as this is concerned, we can think of this as a constant. You can think of this as a constant, okay? Because this angle variation is very rapid compared to this one, okay? So we can write it as n by AC sine theta of t minus some constant, okay? Where k is equal to phi of t equal to constant. Okay. Now expand by using trigonometry sine a plus b or a minus b. Okay. I can write this as en by AC. This is sine theta of t into cos of kt minus, sorry, plus or minus en by AC cos theta of t into sine k. Okay. Now, if you look at this equation carefully, you can find out the product of En and sine theta n. This is magnitude of the noise and this is the component. So En into sine will give us a noise component. Okay, noise component as a quadrature component. So this is a quadrature component. I can write this quadrature component as ns of t by AC cos of k, and here minus En cos theta of t. This is in phase component of noise n of t. or Ni of t, Ni of t, that is N C of t into by divided by AC into sine of k. Okay. Now we can determine directly the noise power spectral density of this input component. So I can write this as okay, G sub del phi of F as, you see, if you think on both sides, the noise power spectral density can be found by taking squares and then adding, isn't it? So here it becomes noise power spectral density of this one and squares of this term. So I can write as cos square of k divided by AC square into GS, okay, sorry, GNS of F minus, here we'll get only the addition, a plus sign only, because the power spectral densities are added, okay, plus sine square of k divided by AC square into GNC of F. And this is the power spectral density of each component, potential phase component, and this is the power spectral density of in phase component. Okay, so and these two are equal. Okay, from the diagram, these two are equal, and so we can write it as, since these two are equal, I am taking it as a common G NC of F, NC of F, okay, by AC square. I'm taking this is square k plus sine square of k. Okay, why? Because GNC of F equal to GNS of F. Power spectral density of in phase component and power spectral density of potential phase component of input noise are equal. That's why I'm taking it as a common. Okay. Now time is running out. Okay. Now we also know that this is a cos square a plus a sine square a, which is equal to 1. So I can write this as G NC of F by AC square. Okay. So once you know the power spec density of input noise component of a, what do you call it? Input noise component of a differentiator, we can find out its output. And here itself you can write the value of GNC. What is the value of GNC of F? GNC of F is nothing but a power spectral density of in phase component of the noise, which is equal to eta. So it is equal to eta. So AC square is a value because GNC of F equal to eta. Okay. Now, what about the output noise power spectral density is simply equal to input noise power spectral density of differentiator. Okay, that is here, which I am writing it as del phi of F into transfer function mod square. Transfer function mod means transfer function of which one? Transfer function of a differentiator. Okay, which is mod transfer function of is j omega square, where okay, transfer function say I'm HD of F equal to j omega, which is equal to transfer function. This is equal to transfer function of differentiator. Okay. So now what is the value here? It is simply equal to eta by AC square and it is simply equal to omega square. Okay. Now what you need to find? You need to find output noise power Pn naught. Simply obtained from its integration. This is a by integrating, and that is one. If you look at the diagram here, no, the power spectral diagram, you need to integrate from minus F to minus W2 plus W. Okay, you need to integrate minus W2 plus W of output noise power spectral density F, and minus W2 plus W and eta by AC square. It is 2 pi F whole square df. Then what do you get here? If you eta by eta and I'm writing it as 2 2 by AC square, and this is simply becomes how much?